Right, thank you. Welcome everyone to what is the first of 3 seminars on the ABI Post-Grenfell Research Program. I'm Jim Glockling, Technical Director of the Fire Protection Association and Risk Authority. And whilst I'm presenting the results of this study, many others have contributed to bring it to this point, and in particular assistance from ABI and its membership who funded the work, Arrow Group Limited for their insight into cladding systems, PSP Architectural, who helped us very extensively with the provision and procurement of materials for this testing. Michael Fox Associates, a forensic investigator of cladding system issues, for his expertise of common flaws noted within the industry. The Risk Authority membership, principally the intervention monitoring and passive working groups who provided technical input to this program, and the FPA's Special Projects Group, who conducted the research very capably in their laboratories. Just a few notes. This is a limited audience webinar, being given really on an embargoed basis a day or two ahead of the official distribution of the work by ABI. And so it won't be downloadable until ABI's press release is made with the full documentation. So the only delay on that is really the testing has only very recently been completed, the draft report's been produced, and really over the next day or two its contents will just be confirmed. Details for everyone involved are given at the end of this presentation. So I can tell you we've got over 500 people subscribed to this webinar, which indicates a very high level of interest in this subject. I hope we can do it justice today. I'm sure you'll all be looking to get out into the sun over lunchtime, so we'll try and stick to timescales accordingly. Now, just for clarification, the work described here is really a fresh eyes look at the main test regime used for cladding systems. It's not a study of any particular material's ability to pass it. So in this case, all the work, unless stated otherwise, has been conducted with materials which are non-combustible in their nature. We really are looking at features of the test regime. It's probably very important to say that some of the criticisms made are really not to do with the test, but at the end of the day, it's how the data gets used and how realistic the test has been in accordance with I suppose the certification of the buildings that they seek to justify safety in. So we need to bear that in mind also. Dominic Lutz, as he's just said, is looking out for any questions, and you're welcome to put those during the webinar in the Q&A section if you're online. Time permitting, we'll try to answer the easy ones. I think also at the end of this, on closing, there'll be a happy sheet, and so if you've enjoyed the webinar, please fill it in. Right, so without further ado, we shall continue, hopefully. Right, now obviously the Grenfell was a particularly tragic event characterized by catastrophic loss of life, extraordinary external fire spread both horizontally and vertically. This is not something which is commonplace. And obviously since then it's highlighted areas of great confusion in the legitimacy of design, material selection, advice, regulations, interpretation, and test and approval methods. And the other dreadful one was the dreadful consequences of stay-put fire policies in buildings that clearly can't support them. Now, following that, FPA and ABI considered a number of research themes. I'm not going to go into these in detail. These are actually all fully reported in the annexes of the report that will be released very shortly. But needless to say, this is really if you like, an amalgamation of everything which we've had concerns about with over the last 5 to 10 years when trying to influence anything to do with building regulations, and particularly in the realms of property protection within the built environment. And some of these are in our gift to change or to lobby for, others less so. But it's quite broad-ranging, and really there's hardly an area untouched by where we might lodge criticism. Now, having considered those research themes, an ABI working group, specially convened, considered them and picked out 3 specific areas for dealing with. One was to do with cladding and the adequacy of current cladding testing regimes to deliver high levels of fire safety in real-world conditions. The next theme was to do with sprinklers. Obviously, we are seeing a proliferation of sprinkler systems in the residential environment. This is not an area which insurers have engaged with greatly as a life safety rather than property protection measure generally. But the focus there is really if systems are going to go in, we would like to encourage them to do the job they're designed to do, but also not create any other additional potential issues for insurers, such as the escape of water. These are obviously additional water-based systems going to buildings where we already have some very poor loss figures to do with escape of water. And then finally, detection. I think it's pretty commonly understood that detection regimes across the whole of the UK do not serve anyone well, and really the fundamental problem behind this is the poor quality of equipment. And we know that better quality equipment now exists that can be much more discerning. And our belief is that at the end of the day, the use of more higher performing equipment could turn the dreadful statistic of 95% of automatically generated alarms being false or unwanted. We could very quickly change that statistic to really an 80% likelihood of there being a fire if they do go off, which adjusts everyone's view of them from the fire and rescue services, insurers and users alike. So we'll be reporting on those on the sprinkler side of things and detection projects in later webinars. So on to cladding test methods. Really, I think you're all probably very familiar with these pictures taken from the standards and the BR reports on how cladding systems are tested. And really, it caters for two types of cladding systems: ETICS, external thermal insulated cladding systems, where basically an insulating layer is bonded in some way to the external envelope of the building, which might be masonry, and then screens are rendered over to provide the mechanical and weather protection onto them. These types of systems do not have voids within them, and it's not uncommon to see systems involving all of the common insulating products as a means of enhancing building thermal performance and modernizing old buildings. So quite a prevalent technique coming up. And we'll be referring back to that later on in this talk. Rain-screen cladding systems are slightly different in the way they are put together, in that there is a void between the insulating layer, which you can see on your screen, and the panel on the front, the rain screen panel. And we'll go into the reasons why these exist, but obviously anyone who's been dealing with fire for a number of years knows that voids do present a particular problem when it comes to the transmission of fire around structures and buildings. So with cladding system testing, really the need for large-scale testing is really a consequence of the use of combustible materials. Otherwise, it would probably be kind of unnecessary. And in this type of detailing, it infers a system that demands a degree of encapsulation of lower performing materials behind higher performing materials. So quite simply put, the built-up system is tested, and hopefully you're trying to keep lower performing materials remote from the fire scenario. And in the documentation associated with it, there's a key phrase here. The test facility allows external cladding systems to be installed as close to typical end-use conditions as possible. And that is, in that sentence, there's an awful lot to be considered about the quality of installation, how it is maintained over time, how it's fitted in the first place, and the through-life performance of the materials not degrading. Really, I think this is where the basis of most of the issues that we're looking at stem from. Do we actually meet this requirement? Is it installed on a test specimen as close to typical end-use conditions as possible? So having considered the test regime with sort of fresh eyes, we came up with sort of 5 key areas to look at for research scrutiny. The first being realism of the fire challenge. It's not uncommon for fire challenges that need to be appreciated to change over time as lifestyles change and loadings change because of the way we live and the materials. So it's not unreasonable to see that on a list. In respect of realism of the installation, you can see on the picture on the right there that this is a perfect form wall with no breaches, when whilst this bit down here where the crib is placed simulates a fire in a room with a window which has broken. Above it, there are no further windows or anything else. We just have the perfect form of the cladding system above, and we might draw some conclusions on that. Third point, in terms of realism in the installation, anything to do with fire. There are a number of requirements for fires to progress, and oxygen provision is one of them. May seem like a strange thing here, but actually this is not uncommon to see where you are trying to test at a smaller scale something that is trying to mimic something in practice that might be much larger. And so we need to consider that. The fourth point, performance of cavity barriers. Cavity barriers are a relatively recent introduction to the built environment, but they have a very valuable job to do for a number of reasons, which I'll describe later, so as not to repeat myself. And then probably one of the most crucial thing, and this is really more about the application of the data itself. So it's to do with the realism of the installation and the application of the data to the end system detailing that's on the building. Now you'll be aware that all throughout the Grenfell inquiry, DCLG commissioned tests. And what we wanted to have a look at was really the detailing of those tests. How realistic are they in comparison to the buildings that they are purporting to assure the safety of? And if there are any differences, why are they different? And could that jeopardize the decisions which are made on the basis of that? So the first point, fuel load relevance to modern materials and lifestyles. The BS8414 test uses a very substantial wood crib. It is a very large fire and by any measure, but it is just wood at the end of the day. Now, from previous insurer research that we did back in about 1999 and 2000, when we were LPC, we recognized after auditing many buildings that about 20% of the calorific value of rooms in residential and office environments, it's not uncommon to see 20% of that made up from plastic materials. So what we did simply here, the crib on the left is the standard 8414 crib. Crib on the right has exactly the same total calorific value, but we've added 20% of its calorific value as plastic rather than wood. We've exchanged it, and to see how they might burn differently. And what we find, we get a longer fire plume. The height of this ceiling here is around 6 meters, and during the course of the test we generally see, difficult thing to judge in some ways, but a general sort of average mean of an extra meter in height on that fire plume. It's also accompanied by increased temperatures. So in a range of thermocouples above this plume, we see the temperature rising, obviously, but flattening after a period of time to a pretty steady state value with a peak of around 650 degrees. When we include plastic in the mix, well, we had to cut this test slightly short, not for any very sensational reasons, but we were, the temperatures in the ceiling space of our laboratory were getting a little bit outside our comfort range. We do have some plastic skylights up there, so this isn't anything to get too worried about, but we do have to curtail the test to stay within the safety requirements of the buildings in which we're doing it. But I think you can see that there we see no abatement in the rate of heat, of temperature increase, even up to the point when we stopped it at around 10 minutes. And we see a peak heat release rate of around 100 degrees more. Now, these may seem like marginal differences, but actually, when we're dealing with materials such as aluminium, which can lose a great deal of its strength quite readily with temperature, they're certainly grounds for further investigation in our mind. Now, and we've got to revert back. This is meant to be a real-life test which demands accuracy. And so we do believe that we can conclude from this that maybe it is time to have a look at the fuel load and see if it's taking into account properly modern materials and lifestyles. The BS8414 test assumes a plume length of around 2 meters. Of course, if it's 3, that can be very different and very meaningful, especially with the presence of penetrations and other windows and other doors within the additional meter that we might actually threaten any system with. So I've mentioned that aluminium is particularly susceptible. I mean, at about at really about 300 degrees, I think it's lost about 50% of its strength. At 550 degrees, it's lost all its strength and is being quite radically consumed. So I think there is a case to answer that another 100 degrees on there might be meaningful too. Now, I'm not saying here that the pass-fail criteria for such a test wouldn't need to change also. So let's not assume that everything that's been tested with a wood crib might automatically now fail with a plastic crib. We're just saying that it's something that needs further consideration in the round and in accordance with the other 4 areas that we're seeking to look at here. There's also the question of what the relevance of this is to other cladding materials. And we have various compressed boards that are used, stone products, other plastic type products. They probably all need to be looked at in the round in the context of this. So really that concludes the first part. Now the second part is particularly interesting. You noted that before that we test in very perfect form. And if we think about what's actually happening there as an encapsulated test where lower performing materials are basically afforded some security behind higher performing materials, do have some concern that the presence of vents, plastic vents with plastic tube, is not incorporated as part of the test because it doesn't take too much thinking to realize that that is a route for fire or flames to access the void very early on in the fire event. At least that's the hypothesis. Especially bearing in mind that they're not tested, but also the external envelope of the building is not considered part of the compartment boundary. So whereas a vent between yourself or your neighbor or an access hall as part of fire compartment boundary, it would have to be appropriately fire stopped to the same fire resisting qualities as the wall itself. These penetrations going out to the external don't need any such fire stopping to be applied to them. So there's no requirement for them to be any stronger than they materially are. And if they're made of plastic, obviously, we know that can fail quite quickly in fire. Now, we have played around with plastic penetrations. Some of you may be aware of the work that we did on timber frame, light timber frame structures. And in this case, on the picture on the left-hand side, I hope you can see my cursor there, showing what happens when you set light to a plastic air brick in the side of a light timber frame building. Now, these things they have no fire performance requirements, only ones to do with ventilation, and they will take a flame within a very short period, around 3 seconds. And actually, we know that many buildings, quite a few buildings have been brought down by these becoming ignited accidentally and both deliberately. And then, as you can see on the picture next to it, that is a route for fire directly into the void that exists within light timber frame buildings. Another study that we did probably about 18 months ago was looking at ETICS system, external thermal insulated systems, which we built against a wall, put a wheelie bin by it, and lit it. Now, this picture shows some vents in it. Now, without those vents present, we actually just got a large melt-out area around where the bin had been. But as soon as you include a vent, obviously, then you start to have scope for chimney effects, essentially, to be set up where fire and heat can enter at the bottom, hot gases can exit via the top, and then that can be quite an aggressive burning regime. And just by the inclusion of vents in this particular case, we turned something that had previously been quite a non-event into the situation that you see on the right-hand side with fire, with an ability to climb from ground floor to the top. So we know that penetrating cladding systems can be problematic. So here's our actual setup. This is a cut-down version of the 841 rig on the left-hand side, spanning about 5 meters in height. But the other thing that we've changed is the combustion chamber. What we've actually done is we've raised it up so that it has some height to it. So when we install a vent, it's mimicking a little more maybe the upstand that you might see in a kitchen. So fire in a kitchen, and at the upstand we have a vent to extract for ventilation purposes. So we can nominally provide a route for fire through this vent if it wishes to do so. And the direction of spread could be into the void could be from two directions. First of all, the flames issuing out the front of the crib and breaking into the void, or up the back. So a pretty realistic scenario. Again, everything that we put in here was fire resistant, with non-combustible, except for the vent itself. So we've used high-performing fireboards, front and back, simply to create the void in this case. And what we find quite simply on these, as these show quite nicely, the yellow circles show where the vent is, and the pictures taken with our thermal imaging camera, even within the first few seconds, we start to see exactly where that vent is because there are hot gases and flame passing through it, and then that will manifest as fire in the void long before fire can break in from the outside, as is the only route from perfect construction. And when we look at, when we take the rig apart, this is the front face showing the remnants of the fire plume, or the marks from the fire plume, with the front place intact. When we remove the front surface, which is simulating the ACM, you can see that there's been quite a healthy fire burning within the void itself quite early on. Now, the consequences of this can be potentially quite far-reaching, because we have a different mode of fire, and quite a legitimate mode of fire entering the compartment itself. It provides an early route for flame passage into void. The plastic provides a fuel source in its own right, and of course that can travel up and it can travel down. It will result in a direct flame attack of the cavity barrier system. Now, I'll talk more on that later, but at the moment I suppose it's safe to assume that cavity barriers could be preheated into their safe position, their closed position, by the allowance for only external heating of the face. And maybe direct attack with flame, they may need to perform slightly differently or be asked to perform slightly quicker. And we mustn't forget that this is a path for both fire ingress and egress between the room, the void, and the outside. So whilst we might, the BS8414 might simulate a kitchen fire, routes in through soft points in the cladding system are as pertinent to a car fire in the car park down below, or a wheelie bin fire indeed. So I think there is a scope here to say that in the respective vents and penetrations, we have not lived up to the ambition of ensuring that the test is real life, and this is something which we will be taking forward. Now, the third one, which is a little different to think about, and we've done it using indicative materials, and this is to do with oxygen provision to the fire itself. Is it a fair test in that respect? We all know that a good way of limiting fire is to suffocate it. But if you're testing in real life, you need to allow excuse me, the provision of oxygen and burning regimes in a manner that is fair and appropriate to the end-use application. And I'm not entirely sure this test meets that. But we thought we'd just to do some indicative testing on indicative materials, just to highlight what we might be on about here. So rain screen cladding systems have to have a void, and that's they have competing requirements. When there's no fire, they need to allow the free movement of air to stop damp issues. They also need to allow water to drain out from behind the rain screen cladding. These are not perfectly sealed systems. They can't be sealed because they need to equalize pressures, which can build up within the void itself so that they don't distort. So a very difficult thing to actually achieve, to say we want the void to be open normally but closed under fire. But we do know that having a void can lead to an issue of chimney effects, as described previously. And I suppose the criticism is that we might have is that BS8414 is often tested with quite well sealed edging, particularly on the sides and on the bottom, and possibly even with an over provisioning of cavity barriers, which might illegitimately limit oxygen provision. This sounds like small details, but this may be relevant, and we need to have a look at it. So just to highlight the point of what we talked about, we ran on this three-sided rig. We just used wood as an indicative combustible material. If you just put that on this rig and you light a fire at the bottom with no void, it climbs up a bit, but it's it's because the flow of gases and re-radiation doesn't really happen in this open environment. It is a relatively slow and well-controlled process. So if we then create a void, which we have done here by including a layer of glass over it, but seal it up well, then obviously, yes, we've got a void, but we're very well sealed. So actually, any fire that you do initiate at the bottom of this will self-extinguish very quickly indeed. But if you create a void and then you allow oxygen in, particularly at the bottom and the top, and allow it to be slightly leaky as a rain screen cladding is, then you can get very, very rapid fire development from bottom to top. And it really is a completely sort of binary change that you see. And I suppose at the end of the day, the question we're asking is the 8414 test more like a suffocated regime, and is it unfairly disallowing the chimney effects to take place within the cladding system? I'm going to leave it there at the moment, just because this is probably getting into a little bit too much detail. But rapid fire spread is very important when considered in association with the performance of cavity barriers, as we'll show now, because there is a rate issue here. Cavity barriers need to operate on a timescale that's coherent with the ignitability of the materials they're trying to separate and the speed of fire spread, which is why this is an associated issue. So on to the fourth bit on performance of cavity barriers. So cavity barriers, people talk often as not as though they've always been in buildings and have always expected to have been in buildings, but that's actually not the case. As short a time ago as 1980, there was no guidance. Following the Knowsley Heights fire, there were amendments made, but we didn't really have the materials to do the job properly. So there was some quite loose requirements, basically saying you should restrict the passage of smoke and hot gases as much as practical. And so I think in there we saw really systems where the void was closed down slightly, but not totally. And then as recent as 2000, we started to see some very clever dedicated products. And then guidance has since been issued from the Centre for Window and Cladding Technology. There are requirements, so rain screen gaps for ventilation, which allow the water to drain and for the void to vent freely, must not restrict the void by more than 50%. So typically a void might be 50 millimeters inside. So a cavity barrier would be allowed to protrude into that space by 25 millimeters, and then under fire it will need to inch-mess or swell to close off the other 25 millimeters. And there's some quite nice products have come on the back of that. So I think we've just been through this. They need to prevent the passage of flame and the passage of heat. How they're installed, I have just like to show a quick video here of how they are installed. They form a break between the insulating layers. You can see in this case protruding proud of it, and under the action of fire, that the front face will inch-mess and close up the gap to the back of the ACM. Now clearly on something like this, the quality of fitting is everything. There's another type which you can see in the right picture there, which is really a steel type of plate coated in inch-messing material, which will then close up those gaps. And in fact, during this test program, we looked at another quite inventive system which uses a combination of inch-messing material and a mesh flame arrestor, which can prevent the passage of flame through it during the inch-messing process. But I think when you look at these things quite closely, we see some funny things. I mean, now is the time to do the detail of what's being installed on buildings. But when we look at some advertising material for some of this cavity barrier, I'm not saying this is bad cavity barrier by any means, but some of the things you see written might make you worry. So in this case, with this product, it says when adopting the fire-resisting testing procedures, technical failure of the integrity of insulation would be deemed to have occurred because flames pass through it, obviously. But a consultancy, I guess under desktop study, have considered the product for rain screen cladding systems and expressed the opinion that it's a practical cavity barrier solution for this application. Now, that may be fine, but it is of interest to someone like ourselves, I would guess, that it's not that those phrases or that phraseology isn't connected with the ignition properties of the materials that they seek to separate. Now, I could well imagine that if it's separating quite high-performing materials, which do not ignite very readily, then it is fine for flames to pass for a bit. But I can also think of some materials, particularly some of the lighter weight vapor membranes, that maybe flames passing for 30, 40 seconds, it would be important to address it. So we built a very nice rig in the lab, and here it is. It is simulates we have a gas fire, we have a vent hood, we have a vent duct, and we pass flame into this cavity here. And our fire stopping, our cavity barrier, is located in this location here. Hopefully you can see my mouse there, but just 2/3 the way up the rig. If I just play this video to you, you'll see the fire break into the void here. There we go, coming through our kitchen duct. And there we see. Now, there we see flames passing the cavity barrier, which they have to do because they activate under the energy, but they pass for probably the best part of 30, maybe 40 seconds in some cases, until eventually it will pinch a mess, and then it will fill that void. I should add that the sides are all sealed here with glass, so we are having this is a proper cutaway look. And there we see, as we've sealed out the route for flame up, it starts to actually suffocate the fire out in this case. So they're very clever devices, don't get me wrong on that, but you can see they do have a performance time of work, and it seems probably slightly strange that their use and their application is not connected to the performance and the materials that we seek to separate. So let's just be very clear, everything in that rig is entirely non-combustible, so there's nothing to burn, but you can imagine some materials put in there where actually the fire would have spread and gone on to the next one. So I think hopefully we've tested a number of different, we've tested a number of different systems just to show what they do, and I think you can see they can perform in a very well indeed. This is this rig post-test. The bottom picture is a view up where you can see the inch-enmeshed cavity barrier pressing on the back of our simulated panel, and on the top one you can see with the front removed, you can see how the front face has swelled to meet the back of our simulated ACM. And the graph below basically shows thermocouples above and below the cavity barrier. Because they introduce a physical barrier as well, what we did, we initially removed the inch-enmeshing strip because the physical barrier is important. And you can see below the barrier and above the barrier, we get these dotted lines here. And as soon as we have the inch-enmeshing strip in place, you can see it gets to a point where it activates around the sort of 30-second mark, which is a good response time. And we can see then temperatures drop immediately. So not really a criticism of the product, but I think there are questions to be raised about its ability to separate certain materials. Right, on to the final part of the test regime that we have here, and I think my feeling is this is one of the most important parts of this work. And at the end of the day, is what is tested representative of the systems that they seek to approve on buildings. When doing a test like this, there can be some confusion about what constitutes part of the rig and what constitutes part of the system under test. And in fact, there are installation detailings that are vital to understand also. So I'll do my best. But at the end of the day, we are talking about aluminium. Here is an image taken from some insurer work conducted in about 2000 on fire spread on curtain wall glazing systems. If you're interested in that work, happy to send out the report on that. Very good piece of work, but these transoms and mullions are very, very strong systems, very large chunks of aluminium, and I think you can see large aluminium gets consumed in fire all too readily on very short timescales. I think this amount of damage happened in about 23 minutes in our office block simulation. when we did that work. So there are some key features about this test, and what we asked Arabs to essentially do was to take one of the DCLG tests and then say, how would this collection of materials actually be installed on a building? And so some of the detailing is a little bit difficult to explain, but we'll do our best. But I think hopefully at the end of it you'll see the point of why we're looking at this. And certainly there are detailings to do with the near edge close to the crib, which you need to consider, are they there in practice? So I'm sorry for falling back on some rather difficult diagrams here, but on the left-hand side, through this next suite of slides, we have our DCLG test replication, and on the right-hand side, we'll call it our typical on-building design. So it uses the same materials, but we probably installed them more in accordance with how they might actually go on a building. So yeah, there I guess we're looking to see, are we submitting a Challenger tank in order to gain an NCAP rating for a Robin Reliant? If there is any misalignment, there might be cause for concern. But in the case of the DCLG test of this type of high-performing ACM panel and high-performing insulation, which was stone wool, so everything basically non-combusting, we can see that the railing system is quite, there's an extra rail assigned to each panel. So we have midpoint support for each panel. And on the right-hand side, we have a railing system, probably more akin to that on a building, where the panels are just supported at their edges. So I think we can see the additional stiffening of any panels required for wind resistance on an in-building type design is often not achieved through the addition of extra rails, but more to the inclusion of panel stiffeners, which are battens which are glued onto the panel, but not affixed to the building itself. So there we see one design change. There's also can be differences in cavity barrier provision and specification. So in the DCLG testing, I think they looked at quite high-performing cavity barriers, giving you 90 minutes, 90/60 and 90/30 rated products for their ability to resist fire and insulate, whereas actually on the requirement for on buildings is 30/15. These are things that need to be understood by anyone conducting a desktop study used to look at the differences. There can be difference also in the positioning of the cavity barriers. So really on our simulation, we put them probably where the floor slab would be, right above the window, and that's probably a reasonable location. But in testing, we see them put in areas much higher up, and probably perhaps an unrealistic location. And the ability of that to influence results might need to be considered also. One of the crucial things is how the ACM panel is actually fastened onto those rails. And this is where we see some of the biggest differences. In the DCLG test, the panels are essentially riveted on to all supports around their edge and along their entire length. This is quite a high level of fixing, and it's not the most common fixing method used out there. So such a system might typically be more often adhered to the front face of the building by a hanger system onto the rails, and that's indeed what we put in front of our test when comparing them. So this is a sort of hook-on system. So very much a lower level of attachment to the railing system, which is already enhanced behind. Also, looking at specific detailing, this is a test of the cladding system, and really the window can form part of this as well. And so there can be very big differences in the near-fire area as to whether the system is going to have recessed windows or windows which are flush with the cladding system. In the system tests as conducted by DCLG, there is an assumption that the window and the cladding, that the windows are flush with the cladding system. And so this very substantial aluminium pod was affixed to the front face of the fire compartment to simulate the presence of a window. Now this is 5mm aluminium, which is quite substantial in size, And again, it will need to be checked as to whether that is realistic in comparison of the window detailing there. Now, for the on-build test, we took a decision to actually look at, well, what if the window was recessed? Then you use something like this, which is really you fold over the ACM panel to actually form the fold back and cover off the bottom of the cladding system back to the front face of and over where the window is. So you can see these small details can have can introduce critical differences to the resilience of the system under test at some quite critical locations. And these are things which I'm not sure whether they get communicated properly and understood properly when people are using the data to ascertain how fit for purpose systems are for buildings. So here we are. Here we see the built-up systems. On the left-hand side, we have the DCLG test. We've used stone wall insulation in here. There you see the railing system, and there you can see the riveted-on panels there. These are, as I mentioned before, cut-down rigs. They're not they're certainly not full-scale 8414 tests. The other thing that we did was on the typical on-building designs, we introduced the other missing components and material. And these are the vapor barriers and cavity vapor barriers that might exist in practice, which do not generally form part of the 8414 test. And there we see the hung-on system on there. And really, the outcome of these tests, when we actually look at how they performed, we can see that side-by-side comparison. Using the standard wood crib, we've introduced none of the differences that we've explored in the previous four phases of work described. But I think you can see that the burnout area is a very controlled consumption of aluminium from the ACM panel. It's not allowed collapse of any features. Nothing's fallen off. It's just been consumed by the temperature. But also, I think there's probably safe to say that the central support has afforded a great deal of additional resilience to the lateral spread of fire in this case. Whereas the typical on-building design, I think you can see from what's lying down on the floor there, was really one of collapse and enhanced lateral spread throughout there. Even though in this particular case we reinforced the fire stopping, the cavity barriers, so we have two layers before there than just the one that we had on the DCLG test replication. A little bit of video just of a key point, I suppose, at the point of collapse. So this is our on-build test. This was the origins of that bit that fell on the floor, but I think you can see how it starts to fall away. It's also interesting to note that we have flaming out the top of the rig, and there's low-level flaming as well. And I think this is from the various breather membranes that were in there, burning in their own right. These are, as I mentioned before, materials that are not generally included in the test. So you can see how really panels are falling off there, breaking away as the hanger system has melted through. It's quite a lightweight hanging system until it eventually falls off in this case. And you can see the residual burning. I think this is pooling possibly of the plastic of the breather membranes down here, and also at the top we're seeing some burning there. Oops, sorry, I didn't mean to. So in terms of cladding tests and real-life system detailing, I think this is quite a critical area. There's absolutely no criticism of how the test houses report what they have done. The reports are very full and very detailed, and they are very clear that the test and the data derived from it is only applicable to the system that has been tested and in the manner it's been put together. So it's not just about the materials. And I think that's where there's a problem with the focus at this moment in time. Everyone is talking about the materials and not how they're actually assembled together. And I think we're showing here that there can be some quite big differences. Potentially unrealistic reinforcement of the over window section, unrealistic support for the ACM panels, and unrealistic sealing against air ingress. Typical features which must allow water out and air in might be missing. Inclusion of things like breather membranes which might be combustible in their own right, a possible provisioning of fire stopping, and in terms of their classification, an over-generous quantities of fire stopping and no vents. So I think you can see there are differences, and it really is a case of going back and doing the detail. When someone says it's tested to 8414, you really need the test report to say, is this the same as what I am asking to judge against? And so really to close, I think one of the things we hope to do here is really to reopen the book on how these systems are tested. But also, it is a very complex area, and there are some strong cases for actually lobbying for non-combustibility. It does simplify everything. Really, built-up system testing is complex if real-world challenges to be appreciated, and we know what they are: inexact installation, wear and tear over time, modification, and really a changing risk environment. You know, it may have been okay to have some building coverings while bins were metal, but now all bins are plastic, and so we can invoke a change in the environment, which then becomes important. And really, the selection of exclusively non-combustible materials really reduces the through-life susceptibility to all these challenges and makes life a lot easier. And you know, here's a photograph taken by one of our surveyors actually of a building. This turns out to be an ETICS building, but clearly a change has happened to expose a lot of polystyrene on that building in a location that's very readily accessible. You know, if you saw other materials in there rather than polystyrene, you might not be too bothered about it. But seeing polystyrene exposed obviously makes life difficult. And so, what is non-combustible? And it's not it can be quite a complex question, because it depends upon the scale of the fire challenge set. I just want to take take an example here from some historic testing, which might prove to be a more beneficial way going forward to provide really key information to insurers and fire engineers alike as to what the differences can be. So here we decided to test, this goes back to some sandwich panel testing done some time ago, and really they can respond, again, that is an encapsulated type system, and here is a case where we have sandwich panels with expanded polystyrene. We know they don't perform too well, but as a test regime, it's a good case. There is protection behind steel paneling, and really the response to any test really depends on the challenge that you give. So if, as we put on the higher levels of fire challenge to them, you know, below 100 kilowatts, to all intents and purposes, it looks non-combustible. Really, the protective encapsulation is working. But as we increase the heat release rate, then the polystyrene starts to participate over and above the energy supplied by, in this case, a gas burner, which is the red line. And then by the time we get up to 500 kilowatts, it really is the major contributor of heat to that fire. And so instantly you can see from a test like this, very simple test, the contribution made for a range of challenges, and it's nice data. We compare that with a sandwich panel with a stone wall content, something which really is very inert to fire indeed. You can see that there's no notable contribution by the insulated panel over the entire range of the fire challenge energies. And in my mind, this is a nice, informative way of providing information of the true combustibility of materials under duress that rely upon an encapsulation method. And these are some of the thoughts that we can feed in to any review of the BS 8414 program. So really, just to finish off, the work will be presented to BSI with a view to instigating a review of how cladding systems are tested. It will be presented to the Hacker Review, Grenfell Inquiry, and BRAC, the Building Regulations Advisory Council, for consideration. I think we will be using it as to support a case for the prescription of non-combustible products in high-hazard applications, including multi-story buildings. And it could be used to support a case for understanding whether the government's appraisal of the population of at-risk buildings is actually well-founded. And maybe the future work that we might focus on the impact of identified challenges in an environment of limited combustibility. So there'll be two further webinars looking at the other elements of sprinkler protection and also yes, sorry, I'm just reading some of the questions coming in. Two other webinars, one on sprinkler and one on the detection systems as well. So I'm just going to take a look at the questions which are coming. I think we've just got one actually, which is actually from the sponsors of the work, to really just to remind you that to embargo the information contained in this webinar until the report has gone out. And there'll be a very comprehensive media briefing from ABI on this work. So we've finished just a little bit ahead of time. I hope that doesn't mean that I've rushed, but I'd certainly like to thank you for tuning into this. We've had a very, very good turnout, a very high percentage of those who subscribed to it. And if any further information is required, please, you're welcome to contact on specific to this work, contact Laura Hughes at ABI. And if any of you out there are not members of Risk Authority but would like to know more about it, then please have a look at our website, have a look at the membership benefits pack, and contact Dominic Lukes. So if you've enjoyed this, please fill in a happy sheet and say so. I suppose as a balanced approach, I should say that even if you didn't, you should still fill one in. But thank you very much for listening, and I think it's time to go out and enjoy the nice weather out there. Thank you very much.